Hello and welcome to SQL Bits. My name is Terry McCann. I will be your ringleader for this session. And in this session, what we're going to look at is how you do machine learning in Azure Databricks. All right, let's have a look at some slides. Okay, so as I said, my name is Terry McCann. And I am the director of artificial intelligence for a company in the UK. We're a data consultancy. We're actually a sponsor today of SQL Bits, so do go and check us out, and you'll find a whole load of great content from us. So we do a whole load of different bits and pieces, mainly around artificial intelligence and big data. Okay, right, carrying on. Make sure that you do also check us out on YouTube. We've got loads of content on there. And if you want to continue learning about Spark and Databricks and machine learning, check out all the content that we've got there. Okay. So yeah, a bit about me. I'm an MVP for artificial intelligence, and being an MVP just basically means I spend way too much time at events like this and probably not enough time actually doing real work. But we love this stuff, so that's okay, right? Okay. So, what is Spark? Okay, what is Spark? So you can break down Spark into its major components. So this picture here represents what Spark Core is. And so Spark Core is a unified platform which attempts to kind of embed four main concepts. So those four main concepts are SQL or data frames. That's the core structure that we basically encapsulate all data into. Then you've got graph processing. This isn't making fancy visualizations, although Databricks can do that pretty good. This is all about graph processing, so building out a graph database, so where you've got really highly connected data. Then we've got streaming, so where you've got fast data, right? And then that last one there is machine learning, and that's what we're going to look at today. So Spark Core is a core set of APIs and foundation code, and then each one of these just kind of builds up on top of it, right? Okay, so let's talk a little bit about the physical Spark-architecture. Now, that term comes from Simon Whiteley, and I thoroughly recommend you also go and watch Simon's sessions at SQL Bits. Simon's our director of engineering. Go and check out his sessions too. They'll be full of awful puns like Spark-architecture, right? But looking at that, okay, so what we've got at the top there is we're working with a cluster of data, a distributed cluster of machines, okay? So not just one big machine, but lots of machines all scaled out. And in that configuration, we will have a driver and we will have multiple workers. We could have 2, we could have 4, we could have 6,000. It really depends on what you're trying to do, how much data you're trying to process, how complex the problem is. And so we've got a worker, we've got a driver that basically controls everything we're doing. And we've got a series of workers. And each one of those workers has an executor on it. And that executor is responsible for actually doing the tasks, okay? And one thing to bear in mind is whatever you're working with here is Spark runs on a Java virtual machine. And that's really important when it comes to talk about machine learning, primarily because if you're trying to just lift and shift your pure Python machine learning code and run it on Databricks, sure, it's going to run. We can run it, but it's never going to take advantage of every one of those executors. And that is because Python doesn't natively run inside the JVM, it has to be exchanged into Py4j. Right, we've got way more about this kind of stuff on YouTube, so go and check that out there, or check out our blogs if you want to know more. But basically, we can't run it in the same way. So we need something else. We need a different library, such as a SparkML, which is what we're going to come to talk about, okay? Right, so let's think a little bit about how a query actually works, okay? So you'll be looking to try and manage your Spark cluster, okay? So you'll need a cluster manager. And for us, that cluster manager is Databricks, okay? It is responsible for orchestrating all of our data, for our driver, and as well as our workers, okay? We don't have to manage everything. Because Databricks is platform as a service, we just worry about our code. The rest is taken care of, okay? You can choose all different configurations, right? So most recently, Databricks now supports Spark 3, which has a huge amount of optimizations over what Spark 2 had. So loads of great stuff there. Right, so now let's actually look at what this query is going to do, okay? So here we've got our distributed compute. We've got our driver, some workers, and now we're going to try and bring in some data, and that data resides in a HDFS compliant subsystem, such as Azure Data Lake, Blob Storage, Azure Data Lake Gen 2, okay? There we can see we've got a single CSV file, and that has been chunked up into multiple, what we call an extent, okay? An extent is basically a small file that your data has been automatically chunked up into, which enables your data to be read in so much faster, okay? Because think, you've got a scaled out architecture, right? You've got a driver and you've got lots of workers. If you've got one big file and you've got 16 workers, then that one file has to be read entirely by one worker before the rest of them can do anything. Now, chunk that file up into 64 pieces, and each one of those 16 can read in one of those files in parallel. So you can read 16 things at once, right? It's going to be so much better, so much faster. Okay. So what happens is when you write a query, you'll execute your query, your driver will go, right, I need to get this data, and it will actually go to each one of those extents and bring it all back up onto each of the executors, okay, into memory. There it will do a bit of transformation, whatever you're trying to do. Maybe you're trying to aggregate across, you're trying to do a Mapreduce function. Mapreduce, right? What does that mean? You can think of Mapreduce as basically being, I'm trying to take a function, and that function may be trying to add up a load of stuff. That function may be trying to transform some data, or that function may be as complicated as trying to perform a logistic regression or something like this, okay, trying to predict a binary classifier. And then what I do is I map that to my data, where my data resides, rather than picking all my data up. And then I reduce the results. I look at all of the results and I understand them, and then I give it back to a single worker to push back. So I take a function, I map it to my data, I reduce the results, and then I take it back, okay? That's all Mapreduce is. Sounds fancy, but it's all it's doing, okay? So all of my data is up on my worker, right? And then what I'm going to do is I'm going to shuffle all that data around, answer my query, and then I'm going to push it off to one worker. That one worker is going to be responsible for coming up with my final answer, and then pushing it back off to my driver so that I get an answer back. And we're going to be doing that all using PySpark, but you could use Python, you could use Scala or Java or R or another language which is supported by Databricks, or fundamentally by Apache Spark, okay? Right. So, what is Databricks? All the stuff that we've kind of just discussed then, right? That's all really looking at what is Apache Spark. So now we want to know is what is Databricks? So, Apache Spark is open source. What do you do if you open source all of your code base? Well, you create a company which is fundamentally geared up around making it the easiest possible way to consume Spark, and then you charge a cost for making it work in that way and make it the best possible experience. That is what Databricks is, okay? So, more than that, it is fundamentally a couple of different services. So at the top there, we've got the Workspace. This is a collaborative environment, a notebook-driven environment. So very much like Jupyter Notebooks. Basically, it is Jupyter Notebooks. You've got the Databricks runtime. And so that is a set of common frameworks, common packages that you will be using. So Delta Lake, enabling the Delta Lakehouse, the Data Lakehouse. Have a look at our blogs again around that, if that's a new term. Spark, okay? TensorFlow and PyTorch, so deep learning frameworks. And MLflow, which we'll touch on a little bit, okay? Which is how we can do model management. Underlying that, we've got Azure and we've also got AWS, right? Okay. So it is set out to be this unified data platform, which helps with your data analysts, your data engineering, and your machine learning, right? Everybody kind of working together in this single environment, which is great. But what about machine learning in Azure Databricks? Okay, how do we as data scientists work with Databricks? Because it is different, right? If you've done machine learning before on, say, scikit-learn, XGBoost, even TensorFlow is quite different to the way that you would normally work. But if you've never looked at machine learning before, I think it makes a lot of sense to kind of describe the high-level processes that we're going to go through. So this is called the 7 steps of machine learning. And we'll talk about why there are 8 steps here in a moment, but bear with me, okay? So there's 7 steps of machine learning. So we kick off. We need to gather some data, right? We can't do any machine learning without data. How much data? Massively depends on what you're doing. If you're training a model from scratch, you're probably going to need loads. If you're leveraging transfer learning, where you're taking a pre-trained model already, you might not need much at all. If you want to know the distinction about that, come ask us a question. We're going to prepare that data, right? We're going to visualize it, we're going to understand it, we're going to clean it, we're really going to shape it, because what we're trying to do is get it to generalize to the problem that we are trying to solve. That may be predicting customer churn, that may be trying to cluster our customers. Depends on what you're trying to do, but we need to make our data generalize as much as we can. We're then going to select an algorithm. Something quite generic. If we're trying to predict a numerical value, maybe a regression of some kind, trying to do a classification, maybe something like a decision tree, right? We've got all of these different approaches that we can look at. We'll talk about a couple of them in a little bit, okay? We're going to train a model, right? And so training that model is, I kind of take my data here, right? And I take my algorithm and I kind of like mush these two things together. I tweak a whole load of parameters in there and then out hops my trained machine learning model. Fantastic. That's exactly what we wanted, right? We then need to evaluate it. Have I got a good model? Have I got a bad model? Have I got an awful model? It really depends, right? And we need to understand how we do that. So we need to evaluate it, okay? Then we do hyperparameter tuning. We squeeze as much extra kind of power that we can out of that model. So tweak a few more parameters and really get it working in the best way possible for us. Then we test our prediction, new data with our model, and then we see how well we're doing, right? That's it. Okay, great. That's the 7 steps of machine learning. Thank you. See you later. Oh, but there's one more, right? There's the one that everyone always forgets. And that is that we actually need to productionize this, okay? We need to put this model into production. If we don't put it into production, we're not going to be able to actually ever achieve a return on investment on the work that we've done. No one is going to benefit from it. That is the most important step, okay? If you are working in machine learning and you're not able to put things into production, this is the time you need to be looking at this, okay? Right, let's carry on. So what is machine learning? This is a very formal definition, but it has a couple of really key terms in it. The ones in red there, and I'll call them out as we go. So, machine learning provides systems the ability to automatically learn and improve from experience without being explicitly programmed. Okay? So, we want our system to learn by inferring from our data without being explicitly programmed. So rather than having to code, these great knowledge-based systems of the kind of 80s, what we're looking to do is say, well, this is what my data looks like. Where there are patterns, learn from those patterns. Don't learn from me saying, okay, if this person lives in this postcode, then this, or but also, if they drive this model of car, then it's this, okay? We don't want to do that. We're looking to say, this is my data, and I want to infer from it. I want to automatically learn. Okay. It relies on an underlying hypothesis of creating a model and tries to improve it by fitting more data to it over time. So the key things there, right? We are improving our data by fitting it with more data over time. Now you're going to see that fit keyword loads as we go through the rest of this session. Fitting is that process of taking an algorithm and my data and then training, okay? Think training and fitting, they're the same thing, okay? And fundamentally, we need some data to make this all work. Right. Types of machine learning. So you can often break down machine learning into one of two ways. You have your shallow machine learning and you have deep learning. Today, we're going to focus on how you do shallow machine learning in Azure Databricks, but deep learning is possible. Should you actually do deep learning on a distributed system? Maybe. If you have a reason to use it, then definitely go for it. But if you don't, if you can do all of your processing on one single machine and you don't need to scale out, that will fundamentally be easier. The same goes for shallow machine learning. Should you do this all in Databricks? Maybe not. Really depends on what you're trying to do, okay? So, the distinction between the two. Shallow machine learning, we kick off with some input data, right? Said it a few times, we need data. Then we do this feature extraction, feature engineering, cleaning process. These first two steps are what are known as 80% of all of machine learning is those first two steps. Going back, getting your data, understanding it, cleaning it, producing it, okay? That's 80% of machine learning. In reality, it's probably not. That has shifted an awful lot. There's a lot more that you need to think about. But where people say 80% of machine learning is spent doing that, they say the other 20% is spent complaining about doing that, right? Come and have a look at some of our other sessions and we'll talk about what other tasks actually happen, okay? Then we take some algorithm, maybe it's classification, maybe it's regression, really depends on what we're trying to do, right? And then we get an output. So, very kind of manual on this side, we're looking at tabular data. Over on our deep learning, we're going to take the canonical example, right, of doing convolutional neural networks. Is this a cat? Is it a dog? Is it not, right? And that is possible using an approach called a convolutional neural network. And when we're looking at convolutional nets or convnets, they work in a different way. Our feature extraction, our feature engineering can arguably be kind of handled for us by using many neurons orchestrated in a deep neural network. All right, so some of this stuff can be handled for us and then we get our output. Now, I'm not going to kid you, okay? Don't think that when you're looking at deep learning that there are any silver bullets, right? Because there aren't. If you're working with tabular data, you still need to do all that feature extraction. You need to apply that domain knowledge you have to actually make this work, okay? Great. So, types of machine learning. You can typically break down most shallow machine learning processes into one of these three things: a clustering problem, a regression problem, or a classification problem, okay? Now, clustering. We're looking at plotting two features against each other. Never heard that term before? A feature basically is a column in your data, an attribute in your data. We just call it feature. We basically rebrand most things in machine learning because we try to alienate people from the industry, right? I'm just kidding. Come play with us. We want people to come and play with us. But we have these different terminologies because they're hangovers from the statistical background that has led into machine learning, okay? So our clustering, we're plotting two features, and then we are inferring based on our knowledge what's happening there, okay? Now we have our regression and our classification. If you're looking at something numerical, think regression. If you're looking at something which has a classification, has something you're trying to predict, is it A or B? Is it A, B, C? Is it A and B or B and C? They're all examples of classification, okay? The key difference between clustering and regression and classification is that our clustering has no label, so it is unsupervised. A label or a dependent variable is the thing that we're trying to predict, okay? We don't have anything here that we are trying to predict per se. We are trying to infer from what has happened. Whereas on our regression and our classification, we are trying to predict something. On our regression, that could be how much is somebody going to spend with us? You know, how much time are they going to be looking at this product? How much of this particular YouTube video are they going to watch? On our classification, why did they churn? What went into a churn? Is this new customer going to churn? Are they a VIP customer to us? What's their propensity to spend? Any kind of label, right? Is this product an apple? Is it a pear? Is it an orange? You know, there's a whole load of different things that go into that. And with those, we have labels. We have something we are trying to predict. Therefore, it is supervised, okay? There are many, many other types, but we're just going to talk about those ones today. And in particular, when we look at Databricks, we're going to look at an example using regression, okay? So for our supervised learning, we are going to need to do this. We're going to need to take some data, and we're going to have to train and test and split it to produce our model, and then we're going to evaluate it, right? So this is the steps that we're going to go through. So I'm going to start off, take some data, okay? We're going to split it. 70, 30, 80, 20, 60, 40, stratified. There's a whole load of different approaches you can apply to this splitting. Which one is right? Again, it's all going to come down to what is your data? What is the problem you're trying to solve? Do you have imbalances in your data? Are you looking at fraud? Hopefully your fraud example is you've only got, 1% or less of fraudulent activity. You're 99% where there isn't fraud. Okay, if you have that, then I can build you today, guaranteed, I can build you a 99% accurate machine learning model at predicting fraud, okay? Right, come over and I will guarantee that for you. Because what I'm going to do is I'm going to create something that says everything is not fraud, all right? That is obviously not a good model, is it? If we just always say nothing is fraud. Yes, it's 99% accurate, but accuracy doesn't always mean everything, okay? So we split our data. We take it through our algorithm and out pops that model, right? Now we've held back 30% of our data. Why have we done that? We've held it back so the training process of our model has never seen that data. So we know for every single row what our value should have been, and now we can check it. So we can say, well, with that model, when we thought it was A, was it A? When we thought it was B, was it B? When it was A, it was actually B, okay? And we can build out our evaluation and we can understand how well our model is doing. When we're happy, cool. Let's put that thing into production, right? Here what we do is we take our data, we take our model, and then we run it through, right? New data goes through our model. Okay, and we get some new predictions out the back. Right, here we go. And then we see we get more predictions, okay? Great. So that is your introduction to machine learning. Now let's start talking about Spark ML and why it's a little bit different and what are the key components. So this is loosely those 7 steps, okay, with our 8th step that we actually put it into production. So we're going to gather some data. We're going to pre-process it, going to clean it, do some feature engineering, do a whole load of stuff to it, right? And then out pops our nice clean data set. Now we go into this iterative process of saying, right, what model am I going to use? Okay, I'm trying to do some kind of classification. I go for a decision tree. It doesn't quite do what I want. I try a logistic regression. That's maybe a bit worse. Now I try a naive Bayes, and okay, that kind of works. I'm quite happy with that. Then we go into a bit of model tuning, hyperparameter tuning, okay? Squeezing that extra bit of performance out. Then we evaluate, is our model doing what we expected? Is it a good model? And then we put our model in production, okay? Now, in Spark, we have a couple of key components. So first of all, we have transformers. That transformer is transforming our data, okay? It's going to take a data frame, it's going to produce a new data frame, right? Then we've got estimators. And our estimators are going to take a data frame, they're going to produce a new data frame, but this time they need to be fit, okay? So what that means is, let's say I've got a load of missing values. Let's say age is missing from my column. Now what I could do is I could say fill all ages with the average age, and that would be okay. Or I could impute the missing values, so I could try to infer what they are based on looking at other characteristics in my data, such as whether they're married or not, whether they have children, and all these other factors, and I will try to estimate their age. I will impute that. I can't just immediately do that. I have to look at all my data first and then do it. So an estimator is something that you fit, and then once it's been fit, it becomes a transformer. This might sound really confusing right now, but trust me, when we look at an example, it's gonna be clear, okay? Estimators are also machine learning models. We need to basically fit our model as well. It's an estimator, okay? How well is it doing? Well, that's going to be an evaluator. Before we have an evaluator, we have a pipeline. And our pipeline basically creates this kind of funnel, right? Where you've got your data coming in one end and it's dirty, and then out the other end is coming your trained model and your predictions, okay? And that is what we are striving towards. How do we know that pipeline is doing what we want? Well, we evaluate it, right? Is it a good model? Is it a bad model? If it's a bad model, I go back and I go again, right? But we are trying to understand that, and then we pop it in production. And ideally, we just do that with MLflow, okay? Right, so a little bit more detailed, right? This is our stack. Transformers. They're going to take in a data frame. They're going to produce a new data frame. Data frames are fundamentally immutable, right? We cannot change them, okay? We can create new ones and we can overwrite them, but once they are there, we can't change them themselves. We're going to call transformer a transformer. That might shock you, right? Transformer and a transformer. You get the idea, okay? They're primarily used for pre-processing. Thank you, little error there. Thank you, little warning. So here's an example. Here we've got a transformer called a Regex Tokenizer. What the Regex Tokenizer is doing is it's for natural language processing. It's taking a sequence of text and it's finding every single word based on a little bit of regex, and then it's translating that into an array of individual words. Okay, that's all it's doing. But you can see there we've got this line here: tokenized df is equal to tokenizer.transform, being transformed. There's no fit stage, so it's not an estimator. Okay, we've got our estimators. We're going to fit our estimators. So other things here, examples are things like machine learning. Other examples may be a vector assembler, a vector indexer, or an algorithm. And the reason we need vector indexers and vector assemblers is that the way that Spark works for machine learning, and basically the way that all of machine learning works, is all machine learning is essentially lots and lots and lots of linear algebra, okay? And with that, so we need to do lots and lots of matrix factorization or deep matrix factorization, multiplying one matrix with another, okay? So with that, we create vectors, right? So we're taking a vector. We have all of our data as a vector so that when we run it through our model, we're able to do our matrix multiplications, okay? And lots of machine learning in Spark requires your data to be on a data type called a dense vector. Right, and that dense vector is just a lightweight way of encoding a value as a vector, right? Okay. We take a pipeline. That pipeline orchestrates all of these steps for us, and it says you need to do this, and then this, and then this, and then you're done. And then we evaluate that pipeline. How do we get a good prediction? How do we know? Let's have a look. Right, demo time, everybody, demo time. So what we're going to do is we're going to switch over now to my desktop, and we're going to have a look at a regression example using Databricks and using SparkML. We're going to step through it all so that you can see what is happening. Okay, here we go. Right, we are over at my desktop. And here what you hopefully can see is this is Databricks, okay? If you've not seen Databricks before, this is a notebook. We have a mixture here of markdown cells and we have code cells. I'm going to step you through exactly what we are doing. Right. First of all, I'm importing a couple of libraries. I'm importing a couple of pure Pythonic libraries, Pandas and Seaborn. And the reason I'm doing that is because I'm going to use Pandas potentially to go and grab some data, and I'm going to use Seaborn to visualize that data, okay? So I'm going to import some functions as well, some PySpark functions, and let's have a look. So import these. Now, let's have a look at the data we're working with. So this is a public data set which is hosted by Databricks, thank you Databricks, called bike sharing. Okay, and we have this file here, our.csv, and it contains a whole load of data, right? It's a bit hard to read. Let's import it as a data frame, Spark's main concept, right, for working with data. So we're going to do this. We're going to say spark.read, and that's going to read in our data from this location here, which is a HDFS compliant system, okay? It's got a header on it. It's got, we're going to infer the schema, and that is our data. We can have a look at that, okay? If we add in a display that data frame and run that, here we can see all of the data that we're working with. We've got a date, we've got the season, we've got a whole load of different pieces. And what we're trying to predict is this final column over here, count. And that is the number of bike rentals that have happened in that particular period, okay? That's what we're trying to predict here. So we're doing a regression, right? We're going to cache our data first. So this is our data frame, df.cache, and that's us actually saying, I want to force this data now to reside in memory. Okay, right, moving on. Here's a little bit of a description about the data. You can go and download this notebook from our GitHub. So if you search for Advancing Analytics in GitHub, you will find it, and then you can just download it and step through it, okay? So We can sample our data, take a small sample out and have a look. It's exactly the same as what we were just looking at, right? So first thing that we might want to do is we might want to have a little look at some summary statistics about our data. Fundamentally, we might want to look at the summary statistics of our count column. So we can see here we've got 17,000 observations. So that is 17,000 individual lines of data that we can work with. We can see here, this is the average. The average bike rental is 189. So on an average day, on an average hour, there is 189 bike rentals, okay? There is a standard deviation of 181. So what that basically means that we know that somewhere roughly, if we're thinking that this is a Gaussian distribution, a bell curve, that our data is somewhere between 189 and plus or minus, 2 of 181, okay? So by looking at that, we can see that our data is quite skewed, and that we can assume that 977 there, which is the maximum rentals, is probably an outlier in our data set, and maybe something we want to investigate, or maybe something we want to handle. All of our data is quite nicely structured, so you can see that we don't have many nulls, and we can kind of see here that we have a year's worth of data. Great. So from 2011 to 2012, is that 2 years worth of data? Okay, so the first thing that we want to do is we want to have a look at how well correlated each one of these values is to our count. The count is our label, right? That is what we are trying to predict. So here, this is using a function called df.stat, so a statistical function, and show me how well correlated everything is. So how well is each value correlated with our label, which is count? So you can see here the instant, which is basically just an ID, is surprisingly well correlated, but isn't something that we typically want to use, okay? The season, the year, the month, the hour. So hour, we can see that is quite well correlated. As we move down, the average temperature, quite well correlated as well. And then we have these two down here. We've got two values, casual. Casual is 70% correlated. So what that basically means is that this data is incredibly well correlated. This value is showing us the R squared, the coefficient of determination. If you were to plot this value against another value to show this would be almost quite a blotted straight line. We can briefly show you that with a fun little game called Guess the Correlation. This is one that you can take home, everybody. Play with your friends, play with your family. Let's say sequel here. Okay, let's start a new game. Right, here, so now what we do is we try to guess the correlation. How well correlated is this value with this value? We can see that there's roughly a decent line appearing here. So we could probably say they're about a 0.62. Oh, it's a fairly bad guess there, 0.38. Here we can see they're very well correlated, okay? So a 0.7. 0.8, right? So we can see how well correlated these are. This is what we're talking about when we're building out that correlation plot here, okay? So these two values are potentially quite problematic for us. They may look like really good things to include in our model, but what they actually are is that plus that is equal to this. Okay, so we don't want these. If we add these in, we have what is known as label leak. These two values leak our label, and they're very good predictors, but they're predictors that we would never ever have, okay? So we really don't want to include them. Now we're going to run another function. Now this function here is using pandas, and it's using SNS, which is the shorthand for seaborn, okay? So what this is doing is it's saying, take our data and convert it into a pandas data frame. So by default, Seaborn is a Python-only library. It doesn't work with a data frame. So we have to convert that data frame into something that it does work with, which is pandas. Everything basically works with pandas, okay? Pandas being the most popular data manipulation package for Python. And then I'm going to say, well, SNS here, so Seaborn, create me a pair plot. And what a pair plot is every single value here against every other value and give me a teeny tiny chart for each one of them so that I can visualize what is actually happening and make some comparisons. So I can start to see, okay, where are there trends? Where are there interesting things happening? So here, I can see all of my values for each value against a count. But what about each value against the average temperature? We would assume that as the hours of the day are low, as it's in the night, then our average temperature is lower. But we can just make sure that, we're actually going to prove our assumptions. I don't know where this data is coming from. So our average data, could be different depending on the time zone that we're in, the location that we're in. It could be a hot country or a cold country. These interesting things that we might want to check. So it's doing quite a lot of stuff, so it does take a while. And the other thing you have to bear in mind as well is that although we've got a single Spark job here, all that Spark job is doing is this translation from a Pandas data frame to from a Spark data frame into a Pandas data frame. The rest of the work is entirely being done on the driver node, which is quite a lot of work for just one machine to do. Okay. And that completes, and we get left with this visualization, okay? So what we can start looking at is, right, let's have a look at something like hour. Or rather, if we compare down here, we've got our count and our hour. So how well distributed is our count and our hour? So what we can see here is that as our hour is low, there are hardly any rentals, and as that increases, over lunchtime in the morning, it starts to build up. So we can see why hour is a really good predictor for us. If we look at that registered and that casual against our count, you can see that directly strong correlation there and there that we just don't want. Okay, so we're going to pre-process our data. The first thing we're going to do is going to drop a couple of columns that we don't think are relevant. Okay. That's our data minus our dropped values. Now we're going to do a very basic bit of feature engineering here. I'm going to compute whether or not this was in the morning or in the afternoon. I'm going to say when our hour is less than 12, make this a 1, otherwise a 0. And all that is doing is a little binary flag there to say this value of this data here for hour is in 0 to 23, so 0 based hour. So less than 12 gives us 0 to 11, right? AM versus PM. Okay. Now that we have got our features, we're all engineered, we're all good. Now we're going to look at how we do that first step, right? That train, test, split. Okay. So we're going to use this using random split. We're going to take 70% to go down one way and 30% to go down the other way, okay? So 70% that we're going to train with and 30% that we are going to evaluate with. Breaking down our 17,000 records, 12,000 have gone to be trained, 5,000 have gone to be tested. Okay. Now we get on to looking at our first bits of machine learning, okay? Here we are taking in some transformers. Now what we're going to do is we're going to encapsulate this all as a pipeline. However, if we wanted to, we could actually transform each one of these. So we're going to bring in a vector assembler and a vector indexer. And this vector assembler and vector indexer are going to be what transform our data into a format that Spark is expecting. First of all, we're going to drop the count column and we're going to create an array called feature columns. So now that gives us all of the columns that we are working with minus the count. Now, the reason we don't include the count when we train the model is because we make a really good model when we try to predict our label, when we actually include the label we're trying to predict, right? We don't want to do that. That's a fairly school-ish trick, right? But we are going to create this vector indexer that is going to create that dense vector that we were talking about. We'll have a look at it in a moment. Okay, so we've got these things. They are expecting an input column and an output column, an input column and an output column, okay? So it's going to take some inputs and produce an output. So every time a data frame passes through this, it will expect to find these columns and produce that column, and then find these columns and produce that column, okay? That's just how it works. Right. Our first bit of machine learning, let's bring in a decision tree. Okay, and our decision tree has a load of hyperparameters that we may choose to explain and choose to go through and have a look at each one of them and mess around with them. Maybe we would look at the maximum depth of our tree. By default, it's 5, but maybe we want to push that higher. Maybe we want to have a look at, you know, maybe something here like the number of bins that we have, you know, a whole load of different things that we can change. But we're not going to right now. We're just going to set the defaults. I'm going to set my label to be my count. This is what we're trying to predict. And I'm going to wrap it up into a pipeline. Okay. So this pipeline here is saying I'm going to set my stages. So first, do my assembling, do my indexing, and then do my decision tree, right? And so that is going to give me raw data going in, model coming out the back. Right, now we're going to do our training. This is where we start seeing fit. So now I'm able to call fit on my entire pipeline, and each one is doing those individual transformations. And so what I'm doing here is I'm saying pipeline.fit, this is my training data, and it's going to produce me a pipeline model. Okay, now that pipeline model isn't a data frame, it is a trained model. Okay, so that is now an estimator. I have trained an estimator. Now to transform my data and actually apply my scores and see what's happening, I need to call transform on something. Now it's a decision tree, so we can visualize that decision tree, albeit trying to actually kind of understand what's happening here is quite difficult because it's all been encoded as a single vector. And we have feature 3 here, feature 6, various different decision points, and then a whole load of different outcomes that are coming out the back of this. So this is a decision tree regression. There are different types, and we could use any one of them, okay? Right, let's save our model. So if we save our model, then we can use this again. And we're not just saving the model here, we are saving the pipeline, so saving everything about it, from its input to its output. We can reload this model back in. I do recommend you go and download this notebook and step through it with me as I'm looking at this. So reading that back in, I've got this new model now called save model. This has been read back in. And now I'm going to call this part, this is the crux of it, right? This is taking my model and actually getting some predictions. So now I'm creating this new data frame called predictions.df, and I'm doing that by saying take my model, transform my incoming data, this is the data it's never seen before, and make some predictions, okay? So here's all our data, and this is our data as a vector, okay? This is our data in dense vector format, and this is our prediction. So actual 65, our prediction, actuals 25, our prediction is 65, actual 16, 65, 25, 65, 17, 65. You see this repeating pattern? That is what a decision tree does, right? It's going to land you on one single value. So maybe a decision tree isn't the right thing for us to use. Maybe we want to try something else. We can go and we could do that if we wanted to. Right now, let's evaluate this model. So we're going to use two different evaluation metrics. We're going to use how well correlated our data is, our R squared, this thing, right? Our guess to correlation. And we're going to take the root mean squared error. So what is actually happening here is looking at how well our model predicted against the values that originally it had, working out the distance, and then giving us an average. So at the moment, this model is on average 108 rentals wrong. Now, this notebook is set up that you can go back in and you can tweak a couple of things and get this number right down to roughly about 30, get it between 20 and 30 with a little bit of practice, okay? So go away and do that. Let's have a little look here. Describe our count again. So we know that on average, we get 189 rentals. And we know that at the moment we are wrong by 108. So not great, but certainly we can do some work to improve that, okay? And we can have another quick look again at our predictions here, and we could go back up and we could say, well, actually, I think a gradient boosted tree might be better, or a random forest, or even a linear regression with lasso, or something else might actually be a more appropriate model for us, right? Okay, that is end to end. us training a machine learning model using Spark ML. Okay, let's head back to our slides. Right. So we saw transformers, estimators, pipelines, and we saw our bike regression. We didn't touch much on ML flow, but ML flow gives us the ability to persist those models actually into a model registry and do a bit more there, which is good stuff. Okay, but when should you use Spark? And when should you use Spark for machine learning? So you can typically break machine learning down a bit further into batch and interactive. Batch being where you're taking a load of data, maybe nightly, and you're scoring it, and then you're going to push that off to a decision support system, such as a data warehouse. Interactive being where you need actually something that is instantaneous, that click, 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 right? Somebody on your website, will they buy, will they not? What is their propensity? Should we make a recommendation? Okay, where you have that high concurrency, low latency. We used to say Databricks was not a good option for that. Now, MLflow is changing. At the Spark Summit a couple of weeks back, it was announced that MLflow would change, and with that change would come an interactive service baked into Databricks. When that lands, Spark ML is great for all of these use cases, okay? We can do them all. We can do the customer churn in real time, product recommendations in real time, A/B testing, microsegmentation, propensity to spend. Any one of these things are all up for grabs now because we have that available. So, in summary, SparkML is a bit different. It doesn't work like your traditional XGBoost, TensorFlow models. All of that stuff works slightly differently. But where you have Databricks, where you have your data all in a HDFS-based system, such as data lakes, blob storage, HDFS locally, then Spark is a great way to work with that data. If you want to know more, come and check out our booth, okay? Check out our virtual booth, where we'll be talking about this stuff in more detail. If you want to chat about it in, again, more detail, let us know. We'll set something up. And so I just say that, Apache Spark is great for so many data analytics tasks. Where your data's in the cloud, then your go-to for batch machine learning should be Databricks, okay? Unless there's something different about it or a bit quirky. And with MLflow as a managed service for machine learning inside Databricks, Spark has never been easier to work with and to get your models into production faster. So I'm Terry McCann. Hopefully you've enjoyed me being your ringleader. As I say, I'm the Director of Artificial Intelligence for Advancing Analytics. There's my email address. Please do come and get in contact with me. Love talking about this stuff. I'd love to continue the conversation. And so thanks very much. Enjoy the rest of your conference. And hopefully I will join you for a virtual beer sometime later today. Okay, enjoy. See you later.